Hello everyone, and today I will be covering the applications of integrals to physics. We'll first start with the relationships between position, velocity, and acceleration. As previously learned, we know that position can be derived, and the derivative of position is velocity. The derivative of velocity is acceleration. And using our knowledge of integrals, we can go backwards between these. The integral of acceleration will give you the velocity function plus its initial value. The integral of velocity should get you the position function plus its initial value. Using this knowledge, we're going to go forward and solve some problems using particle motion. So now we will be moving into our first example problem. How far has the automobile traveled in the interval between t equals 0 and t equals 2, given the velocity equation 4 plus 2t cubed? Now, we need the change in position from two values. You should recognize that that is a part of the fundamental theorem of calculus, which states you can get the change in a function from 2 points by integrating its derivative and evaluating it at those 2 points. So we currently have the derivative of that function, of that position function, which would be velocity. So if we integrate velocity and evaluate it from 0 to 2, we should be able to get the change in position. So the integral of 4 plus 2t cubed should get you 4t plus 1 half t to the 4th evaluated from 0 to 2. Now if we are to evaluate that, we should go ahead and get 4 times 2 plus 1 half times 2 to the 4th. The rest will cancel out because it would all be 0, which should get us 8 plus 1 half times 16, because 2 to the 4th is 16, and 8 plus 8 is 16. In this next problem, we have how much work is done by the force in moving the particle from x equals 2 to x equals 1. Work can be calculated by force times distance, change in energy, or the integral of force. Knowing this, we can simply take the integral of the force equation and evaluate it from 1 to 2. So that would be the integral of 4x to the third, which would get you 4 over 4 times x to the 4th, which is simply just x to the 4th, evaluated from 1 to 2. After some evaluation, we get 2 to the 4th minus 1, which is simply 16 minus 1, which is 15. In this next problem, we have what is the magnitude of the change of momentum of the ball from t equals 0 to t equals 0.10. Now, they give us the force equation as alpha t minus beta t squared. Then they give us the constants of alpha and beta. Now, if we substitute these in, we get force equals 400t minus 4000 t squared. Now, we need the change of momentum. And we know that momentum is mass times velocity. Now, if we take into account that force is mass times acceleration, and we know that acceleration is the derivative of velocity, we can simply integrate this to simply get mass times velocity. So if we take the integral of force, or mass times acceleration, we should get mass times velocity. And we don't need to worry about the beginning constant because we're evaluating it from 0 to 0.1. It is a definite integral, so you can ignore that c right there. So, now we're going to take the integral of this force equation to get the change in momentum. So, the integral of this should get you 400 over 2t squared minus 4000 over 3t cubed. Now, if we simplify this down, we should get 200t squared minus 4000 over 3, and the rest would be 0, so we can keep evaluating. We should get 2 minus 4 thirds, which is simply 2 thirds.
And for our next problem, we have to find a possible expression for the position of an object in both the x and y directions. In the problem, we are given that the acceleration in the x direction is equal to 8 meters per second squared, and the acceleration in the y direction is equal to 0 meters per second squared. So, in order to find the velocity in the x direction, we simply integrate the acceleration in the x direction, and we do the same for the y. Remember that integrating a non-zero constant will give us that constant, in this case 8, times t, whereas integrating 0 will just give us a constant. In this case, that constant is notated as d1. So in order to go from velocity to position, we just do as we've done before, and we integrate our velocity equations. Again, let me reiterate that integrating some constant is going to give us that constant times t, in this case c1 times t or d1 times t, and then because we integrated, we have to tack on another constant, in this case notated as c2 and d2. If you come across a problem like this that is a word problem, then this right here would be your answer. However, in the case of a multiple choice problem, you may have to substitute in certain values for your constants in order to find an answer choice that fits with one of the available selections. In other words, try plugging in simple values like 0 and 1 for your C1 and C2 and D1 and D2 in order to produce an equation or set of equations that matches one of the given answer choices. But be wary that the constants can be any constant, like pi or e, so don't let that trip you up. And for this next problem, we are asked to find the change in potential energy of a particle from x equals x1 to x equals x2, where x1 and x2 are just arbitrary constants. The force equation that we are going to be working with this problem is F equals negative k over x cubed, where k is yet another arbitrary constant. In order to solve this problem, recall that the integral of the force is simply the change in energy. In this case, that energy being potential energy. So, since we are trying to find the change in energy from x1 to x2, we simply set up a definite integral from x1 to x2, integrating the force. Then we simply plug in the force equation that was given to us, and we rearrange our integrand so that way we can perform the anti-power rule. Then we anti-differentiate and evaluate. And then, after some simplification, we are left with negative 1/2 k times the quantity of 1 over x2 squared minus 1 over x1 squared. And for our final problem, we are asked to find the potential energy of the nonlinear spring when the compression distance x is x0. In this case, x0 is just an arbitrary constant. Because this is a spring, and we are asked to find the potential energy of a spring, which is an elastic system, you might be quick to think that we can find the potential energy using the equation given our formula sheet, which is that potential energy, or elastic potential energy in particular, is 1/2 kx squared. However, if we look back at the problem description, this is a nonlinear spring, which makes this spring system unideal, which means that this formula does not apply. So don't just plug in x0 and call it a day. Instead, we must remember that potential energy, whenever we're giving a force equation that is in terms of displacement, the integral of the force equation is equal to potential energy. And do recognize that this is a different relationship because our force is in terms of displacement as opposed to time. So in our problem, we are given that the force equation in terms of displacement is equal to kx squared, where k is just another arbitrary constant. Knowing all this, in order to find the potential energy at x0, we must integrate our force equation from 0 to x0. Then we simply plug in our force equation and anti-differentiate. Then we simplify until we get that our potential energy equals 1/3 times k times x0 cubed. That's all we have for you today. Thank you so much for watching and listening to our explanation to these problems. Hopefully you found this helpful. Have a great rest of your day.